Okay, the acid-base properties of ions and salts. Some ions can act as bases, like the hydrogen carbonate ion. It's in that list, that table of weak bases. And they can do that because they are the conjugate base of a weak acid. So hydrogen carbonate ion can take a hydrogen ion from water to leave hydroxide ion, and then it forms carbonic acid. So this is the base, this is the acid, this is the conjugate acid, and this is the conjugate base. The conjugate acid can act as an acid, right? So we recognize that as an acid. So this is something important to remember. And this is why we use net ionic equations so much in Chem 1B, because usually we're only interested in one of the ions. The other one is a spectator, but it has to be there. So any ion has to be paired with a counter ion to make a neutral compound that's then dissolved in water. You can't have a solution of sodium ions. There's got to be a negative ion in there, chloride or hydroxide or something. So if we use sodium hydrogen carbonate, which is baking soda, this will dissolve to form sodium ions and hydrogen carbonate ions. The hydrogen carbonate ion is a weak base. So a solution of sodium bicarbonate or baking soda will be basic. And that's why we have shakers of sodium bicarbonate out here for acid spills, because you can toss that on the acid and it will neutralize the acid. Any questions? This can be a bit much to get your mind around, because acids and bases are just like different sides of the same coin, right? And so you're just looking at, well, does it have the hydrogen ion or not? One way it's an acid, one way it's a base. And so we have to be okay with them going back and forth like that. So we can think of any anion as the conjugate base of an acid. So if we call our anion A-, that's the conjugate base of the acid HA. Because to take a base and make it into an conjugate acid, you add hydrogen ion. To take an acid and make it into the conjugate base, you subtract hydrogen ion. So if we look at NO3-, this is the conjugate base of nitric acid. This is the acid, that's the conjugate base. So we can think of any ion as a conjugate base, but not every ion acts as a base. It depends on the strength of this acid. The conjugate base of a weak acid will be a weak base. The conjugate base of a strong acid will be pH neutral. Because if we think about hydrochloric acid, right? This is a strong acid, ionizes completely to form hydrogen ions and chloride ions. The reverse reaction doesn't happen at all. They separate and they will not go back together unless you evaporate all the water out. So this is the conjugate base of a strong acid. It has no affinity for the hydrogen ion. It has no ability to take up a hydrogen ion. So this is not going to act as an acid or a base in solution. It's not going to affect the pH of the solution. Does that make sense? The weaker the acid, the stronger the conjugate base. It's kind of a push me, pull you kind of thing. If one is weaker, the other is stronger. If this one's stronger, the other one's weaker. And so what happens when you get a strong acid, the strong acid is so strong that the conjugate base doesn't act as a base at all. That's sort of the extreme. So chloride, pH neutral because HCl is a strong acid. But fluoride is the conjugate base of hydrofluoric acid, which is a weak acid. So our weak acid ionizes partially. So this is an equilibrium process. And so fluoride can take a hydrogen ion from hydronium to remake water and reproduce HF. So it goes both ways. Any questions? It's one of those things that when you see it, it's really simple. But if you don't see it, it's like weird. Yes?
What is affinity?
Affinity, like attraction for. Yeah. So the fluoride, in order to form HF, the fluoride and a hydrogen ion must be able to bond with each other. So affinity is not a specific term for this. It's just out of the thesaurus in my brain, it's the word I picked. But the hydrogen ion and the fluoride ion like each other enough that they will get together and reform hydrogen fluoride. And then they may decide to split up again, and they can go back and forth. Good question. Anybody else? So this figure illustrates the relationships of the different acids and bases. So up here, we have the strong acids, well, some of them, HCl, H2SO4, HNO3, and hydronium is also considered a strong acid. So HCl, its conjugate base, is chloride ion. That's pH neutral. The conjugate base of sulfuric acid, hydrogen sulfate, is pH neutral. The conjugate base of nitric acid, nitrate, is pH neutral, because these do not go the other way. The conjugate base of hydronium ion is water. Well, that's not an all-the-way reaction. Water is amphoteric. It can act as an acid or as a base. And so here, it's a very weak base. As we go down here, the acids get weaker and weaker and weaker, and their conjugate bases get stronger and stronger. We get down to the bottom, and we see things like hydroxide ion, so that could be sodium hydroxide. Sulfide ion, could be potassium sulfide, or O2 minus oxide. These are strong bases, and so their conjugate acids are not acids at all. They're negligible, don't act as acids. So classify each anion as a weak base or pH neutral. What we want to do is we want to write the formula for the conjugate acid and identify whether it is a strong acid or a weak acid. So how do we make this first one into the conjugate acid? We add hydrogen. So HCHO2. We're adding H plus, and so the charge goes to neutral. Is that a strong acid? No. So there's 6 strong acids. Any other acid is a weak acid, right? So you don't even have to know what that acid is. It's not one of the 6 strong ones, so it's weak. If this is a weak acid, what does that tell us about its conjugate base? It's a weak base. So this guy, whoops, writing in the wrong place. This guy is a weak base. How about this? ClO4 minus, perchlorate ion. Write the formula for the acid. What do we get? HClO4. Is that a strong acid? Yes, it's one of the 6 strong acids. That's a strong acid. So what does that tell us about its ion? pH. Now, I somehow paused it in there somewhere, but I've not been successful at uploading these to YouTube anyway, so I don't think it really matters. So anions can be weak bases, right? We can determine the pH of the solution that acts as a weak base, but we need to know what Kb is for it. So we can derive the relationship between Ka and Kb. So here we have the chemical equation describing the ionization of the acid. That's what we use for Ka. So Ka is the hydronium ion concentration times the ion concentration divided by Ha. This shows the anion acting as a base to form hydroxide ions. So that's the reaction for Kb. So Kb is equal to OH minus times Ha divided by A minus. So we want to know how these are related to each other. So here I've got A minus over HA. Here I've got HA over A minus. If I can rearrange these so they both are equal to the same thing, then they'll be equal to each other. So for this guy, if I take the hydronium ion concentration and divide both sides, Ka over the hydronium ion concentration is equal to A minus over HA. Over here, this is upside down. So there's, different ways to think about that. See if I can make some sense here. No, not white. I want a different color. So if I separate this equality at the equal sign and between the numerator and denominator of any fractions, what's the denominator here? It's 1, right? So it's just a 1. I can take anything up here and just move it down there. I can take anything over here and move it up there, or anything from up here and move it down there. And I can just shift stuff and without having to write out a whole bunch of stuff. So that's what I'm going to do. So I'm going to put A minus on the top over there, and HA, that's an H, on the bottom, and that's going to be equal to the hydroxide ion concentration divided by Kb. And if you want to see how that's, you want me to prove that to you later, I'd be happy to. So A minus over HA, A minus over HA, so we can say Ka over the hydronium ion concentration is equal to the hydroxide ion concentration divided by Kb. Well, that doesn't look very helpful, does it? Let's cross multiply that. Ka times Kb equals the hydronium ion concentration move over times the hydroxide ion concentration. And what does this equal? Kw, right? Which is 1 times 10 to the minus 14. So we can say that Ka times Kb equals Kw, which equals 1 times 10 to the minus 14 at room temperature. So if we're looking at the conjugate base of a weak acid, and we're trying to determine the pH of a solution, and we're trying to look at, okay, this is the concentration, and it goes over here, and I need Kb, but I can only find Ka. Kw divided by Ka is Kb. So let's find the pH of a 0.25 molar sodium acetate solution. And we're given a Ka. So, nope. So, we look at this guy. This is an ionic compound. It has sodium ion and acetate ion. Right? Na plus, C2, H3, O2 minus. If we put a hydrogen ion on that, it becomes an acid. And that is acetic acid. Well, I don't know why I did that. Okay, and this is the Ka for acetic acid. But we're looking at an acetate solution. That's a conjugate base. So, does the sodium ion do anything here? No. It was just the companion for acetate. Because it's like some party where you have to bring a date. They won't let you go by yourself, right? You have to bring somebody. It doesn't matter who they are. You don't have to even look at them the rest of the time. But you have to come in the door with them, right? So acetate brought sodium and then just blows him off. So we'll write the base equation for acetate ion. So this reacts with water to form HC2H3O2 plus hydroxide ion. You can't just write the acid ionization equation and make it backwards. It doesn't work. Because there's no hydronium ion in here. There's hydroxide ion. So if we make our ice table, We're told that the initial concentration of sodium acetate is 0.250. Oh, we don't really need the M there. 0.250. Came in with sodium, but that doesn't matter. Initial concentration of acetic acid is going to be 0. Hydroxide, essentially 0. So then this will decrease by X. These guys will increase by X. And so the equilibrium relationship is 0.250 minus X, X and X. So Kb is going to equal X squared over 0.250 minus X. But we don't have Kb. We have Ka. So we have to use this. This would be a good time for a different color. Kb is going to equal 1 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5. Make sure that you are using scientific notation correctly on your calculator or you will get the wrong answer. I'm getting 5.5 forever times 10 minus 10. So that's what this guy is equal to. 5 point, I'm going to write it out, 5, 5, should have 2, 5, 5, 6 times 10 to the minus 10. This is a small equilibrium constant. 0.25 is a relatively large concentration. So X is small is probably going to work here. But you can also do it on your solver. So X is going to equal the square root of 0.25 times Kb. Anybody else get that? Okay. That is so small compared to 0.25 that I don't even need to do the math. It's obviously less than 5%. It's got 4 zeros before the first significant figure, so just sig figs, when you subtract there, it wouldn't change it at all. What does X equal? The hydroxide ion concentration. We want the pH. So, whoops, pH is going to be equal to 14 minus POH, which is equal to 14 plus the log of our hydroxide ion concentration down there. And I'm getting 9.0713. Probably 2 sig figs based on the Ka value. So pH is 9.07. Is that a reasonable pH? Yeah. because this is a weak base. The pH better be higher than 7. Otherwise, it's not a weak base, right? It'd be an acid. Any questions? .07. Which anion acts as a weak base? C. What we're looking for there is we want to look at the conjugate acid of these, which is hydrochloric acid, hydrobromic acid, hydrofluoric acid, and then ask ourselves, are those strong or weak? Well, the first two are strong acids. The last one's a weak acid. So that means that this acts as a weak base. Okay, so any questions about anions acting as weak bases? Yes?
Is it something different when we were talking about one side it was like strong, the other side was weak?
It's related.
Because at first I thought I would be looking for the strong acid one.
So the stronger the acid, the weaker the base. So here, whoops. Good grief. HCl is a strong acid. HBr is a strong acid. HF is a weak acid. Strong acids ionize completely. So chloride is not attractive to the hydrogen ion to remake hydrogen chloride in the solution. So it's not going to act as a base because there's no equilibrium. This just goes one way. Whereas with the weak acid, we have an equilibrium. It doesn't dissociate, it doesn't ionize completely. And so if we just have this, it could pick up hydrogen ions from water. Okay? Yeah, good question. Any other questions about the bases? So anions can act as weak bases, cations can act as weak acids. There's 3 categories. We have pH neutral cations. These are the cations from strong bases. Strong bases dissociate completely. So they're counter ions. The cations that we're talking about here are not going to ionize water. So examples would be calcium, sodium, potassium. Counter ions of strong bases. It's kind of like the counter ions of the strong acids didn't work as bases. Then we have cations that are conjugate acids of weak bases. So a cation that is a conjugate acid of a weak base is a weak acid. Not confusing at all. Acid, conjugate base. Base, conjugate acid. Right? Which one you call the conjugate is just which side of the equation you're looking at. They're an acid-base pair that are related to each other. So the cations that get formed from non-ionic weak bases, like ammonia or any of the amines, can add a proton. Sorry, a cation can be formed from a non-ionic base by adding a proton to its formula. Yes, and then this can act as an acid. And the pH of the solution can be calculated using Ka. Because this is from a base, what you're going to find in the tables is Kb. Because it's most likely a stronger weak base than it is an acid. Same process that we just went through with the anions. And then there's this third group. These are weird. Small, highly charged, there's a typo. Highly charged metals such as Al3+, Fe3+, can form weakly acidic solutions. So how do they do that? Well, the aluminum ion here can get hydrated. So 6 water molecules are going to come and hang around it. When ions dissolve in solution, they do get hydrated. What's different about this is that the hydrated ion can act as a Bronsted-Lowry acid. So this can donate a hydrogen ion to water, producing hydronium ion. So it's acting as an acid. So this is the ball and stick model. And so what we see is one of these hydrogens gets donated to a water molecule. So now it's missing one over here. And this is the hydronium ion. And this has a weird formula now because it's got 1, 2, 3, 4, 5 water molecules around it and 1 hydroxide. It lost a proton, so its charge changed overall as well. I see some very suspicious, skeptical looks. What is this? It is weird. This is weird. They do this because they are very small, so 6 water molecules can get around them. And they have a high charge. If you have a low charge, not going to happen. If you have a bigger ion with a high charge, it's not going to happen. They have to be small and highly charged. So really, it's just these two that we need to worry about, aluminum and iron 3. So classify each cation as a weak acid or pH neutral. We want to look at the conjugate base of it. So lithium gosh, can we write a conjugate acid for lithium? To write the conjugate acid, no, we need the conjugate base. Anyway. What base does this come from? Lithium hydroxide. It can hurt your head in this class. Lithium hydroxide dissociates completely because it's a strong base. All of the metal hydroxides, the ionic compounds, will separate. So is this going to act as an acid then? No. That one will be pH neutral. What about this guy? We couldn't take a hydrogen ion off of that because it didn't have a hydrogen ion. But this one has hydrogen ions. So if we take a hydrogen ion off of that, we get CH3NH2. This is ammonia where it swapped out hydrogen for something else. We have carbons and hydrogens and one nitrogen. And that's all you need to know to recognize that as a weak base. It's got carbons and hydrogens and a nitrogen. It's a weak base. So because this is a weak base, that makes its ion a weak acid. And then there's this guy.
It's an acid.
It does act as an acid. Because it's one of the two that I expect you to remember. Al3 plus, Fe3 plus. They get water molecules around them, and then they can lose one hydrogen ion. Any questions? Hmm? Yeah, I did do that, didn't I? Oh.
There we go.
Wonder, I don't know. We don't need to know. We don't need to know. Okay, so we've looked at cations and anions separately. Now we're going to look at salt solutions. So we're going to have to look at the anion and the cation in the salt. So the pH will depend on the specific cation and anion that are involved. So there's different combinations possible. You can have a salt where neither the cation nor the anion acts as an acid or a base, right? So these are going to be pH neutral. The cation is the counterion of a strong base. The anion is the conjugate base of a strong acid. So things like sodium chloride, calcium nitrate, potassium bromide, Br minus from HBr, a strong acid. Potassium from KOH, a strong base. So when these dissolve, they don't alter the pH of the solution. Then we can have a salt where the cation does not act as an acid, but the anion does act as a base. So we're going to end up with a basic solution. So this will look like we've got the cation being the counterion of a strong base, the anion being the conjugate base of a weak acid. So here, sodium fluoride. Well, sodium is the counterion of NaOH, a strong base. That one's going to be neutral. F minus is the conjugate base of a weak acid. That makes this a weak base. These are the sorts of problems that you really should be talking to yourself in your head during an exam. And before the exam, when you're just learning about it, actually say the words out loud. Because it's so easy to go the wrong direction, right? It might even help to just write it down. Whatever you need to do. We can have salts where the cation acts as an acid and the anion does not act as a base. So this is going to give us an acidic solution. So the cation is the conjugate acid of a weak base, or it could be one of those small highly charged metals, Fe3 plus or Al3 plus. And the anion is the conjugate base of a strong acid. I would not want to just look at this and say whether the solution is acidic or basic. I would talk through it in my head. So let's look at this guy. We got ammonium and bromide. So this comes from HBr, strong acid. This isn't going to do anything. This comes from NH3, weak base. That means that this is a weak acid. You guys okay with that? You can do the same thing with these other examples. And then we've got the fun one, where the cation does act as an acid and the anion does act as a base. And so here, the solution pH will depend on the relative strengths. So we compare the Ka of the acid to the Kb of the base, and the higher K value dominates. So these are examples. AlC2H3O2. Here we have the aluminum ion. That acts as an acid because it's one of those small, highly charged guys. C2H3O2 minus comes from acetic acid, a weak acid. So this will act as a base, that will act as an acid. Unless we have the Ka and Kb values for those guys, we won't know which one wins. So this summarizes the different possibilities. Our cations can be conjugate acids of weak bases, small highly charged metal ions, or counter ions of strong bases. The anions could be the conjugate base of a strong acid or a weak acid. And so when you put these two together, these combinations will give you acidic, this will give you basic. These two over here depends on the relative strengths. Okay, determine if the solution formed by each salt is acidic, basic, or neutral. So what do we want to do? We want to look at the two ions that are present and see what their conjugates are, right? So this one, think back to Chem 1A, where we only ever had two ions. So the metal is the first ion, and everything else is the second one. So this is sodium ion and hydrogen carbonate ion. This is the counter ion of a strong base, sodium hydroxide. So that's going to be neutral. What acid does this come from? Carbonic acid, H2CO3. It isn't a strong acid, so it must be a weak acid. So this acts as a base. So the solution will be basic. Let's look at this one. Don't let this intimidate you. We're looking for two ions. This one's a mess at the beginning, so maybe let's just kind of look at the end and see if we see something familiar. Chloride? So we've got chloride and the other part that's ammonium, but it swapped one of its hydrogen for something fancier. So it looks different, but it's really very similar. So in order to see if the cation acts as an acid, we want to see what kind of a base did it come from. It's not a strong base. It's not sodium hydroxide, potassium hydroxide, something hydroxide. It's a weak base. because this is a weak base, this is what? A weak acid. So this one is a weak acid. Then we have to check the other guy. What acid does that come from? HCl, which is a strong acid. So that one's going to be neutral. Okay? It's not rocket surgery, but it can be really confusing. KNO3. We've got potassium ion and nitrate ion. Is potassium related to a strong base or a weak base?
Strong base.
Strong base. It's the counter ion for KOH, right? So because this is the counter ion of a strong base, that means it's neutral. What about this?
Strong acid.
That's the conjugate base of a strong acid, so also has no effect on pH. So that solution is neutral. You have a question forming or no?
I got the next one.
Oh, cool. So the next one, we've got Fe3+. We can figure out the charge by knowing that nitrate's -1 and there's 3 of them. And then we've got nitrate ion. So this one, we should just recognize that's one of those two weirdos. This is a weak acid. Fe3+, Al3+. And then this one is not changed from what it was up here. It is still the conjugate base of a strong acid, so that one doesn't do anything. And so D will make an acidic solution. Any questions? Isn't that fun? Yeah.
I have a question about the bicarbonate ion. I just realized that it was amphoteric after a long time of thinking of it one way as, the
Yes, it
conjugate
is.
base of an
It is
acid.
amphoteric.
So is it going to be situationally dependent on, the question that we get where we have to observe the bicarbonate as either a base or going back into its form of the carbonate ion? Probably given with our K values, right? Because I thought of
Well,
that as like being the middle intermediate thing.
Right.
that could go
This
both
is the
ways.
middle,
Yeah.
right? So if we have H2CO3, that can lose a hydrogen ion and give us HCO3 minus. And this can lose a hydrogen ion and give us CO3 2 minus. No, what am I doing? There it is. So this is a weak acid. The conjugate base of a weak acid can act as a base. This, though, can also act as an acid. Carbonate ion is the conjugate base of a weak acid. This can only act as a base. But hydrogen carbonate can act as both. And this is the key to the bicarbonate buffer system that your body uses. And carbon dioxide is part of that because carbonic acid is unstable and it will come apart into CO2 and water. This actually is an equilibrium. So CO2 affects the pH of water or blood or whatever it is. Basic, acidic, neutral, acidic. Which of these forms an acidic solution when dissolved in water? So we're looking for an acid, right? So it's going to be the cation. Is the cation acidic? Potassium ion is the counterion of a strong base, potassium hydroxide. Sodium ion, counterion of a strong base, sodium hydroxide. What about ammonium? That's the conjugate acid of a weak base, and so this is the one that will be acidic.